In this video, we will answer two seemingly strange questions. The first is, are there real numbers larger than any rational number? The second, which is equivalent to the first, asks, are there positive real numbers which are less than any positive rational number? These numbers, if they exist, are called infinitesimal numbers. As the intuition suggests, both questions have a negative answer and are, in fact, encompassed by the so-called Archimedean property of real numbers. This property states that given a number x, there exists always a natural number n greater than x. The proof of the Archimedean property is simple and proceeds by contradiction. So let's help with the figure. So suppose that there is a number x which is larger than any natural number, so 0, 1, 2, etc. So we may imagine that the set of naturals is at left of this x. In particular, this x would be an upper bound for the set. And therefore, since in real numbers, an upper bounded set has the best upper bound, which is the supremum of the set, that would be the number, say, omega, the supremum of the set of naturals. Now, according to the characteristics of this omega, whenever we take a number b, which is strictly less than omega, there is always a number of the set, in this case a natural number, at right of b. So there would be a natural here. Now, the trick consists in taking b so close to omega in such a way that even if n is at the left of omega, n plus 1 is at right. So there would be a natural at right of omega, which is the supremum of the set of naturals, and this would be a contradiction. In fact, it is sufficient to take as b omega minus 1. Because in this case, there would be a natural larger than omega minus 1. So there would be an n such that n is larger than omega minus 1. And this means that n plus 1 would be strictly larger than omega. So it would be about here. And this would be a contradiction. The Archimedean property comes into play whenever we want to establish the existence of at least one natural number larger than a given real number x. For example, this is useful in the definition of limit. Here, we illustrate an immediate consequence of this property, this so-called density property of rational numbers into real numbers. This property states that given any two real numbers a and b, with a less than b, there is always a rational number between these two. Now, to prove this property, we use the Archimedean property of real numbers. Again, let's help with the figure. For simplicity, we may assume that a and b are both positive. So the idea is to take the length of this interval, which is b minus a, which is, let's say, about here, and look for a fraction of type 1 over n, which is just smaller than that 1 over b minus a. So then, by taking multiples of these fractions, so repeating at regular intervals of length 1 over n these points, sooner or later we will just have a fit on that interval. Now, the existence of a natural such that 1 over n is less than b minus a is, of course, equivalent to say that there exists a natural greater than 1 over b minus a, and this comes from the Archimedean property of R. So now that we are sure that this fraction exists, we take multiples of these fractions, so 1 over n, 2 over n, 3 over n, and so on. Well, sooner or later, it will happen that the fraction m over n is at the left of a, but the next one will be at the right of a. So let's say that m plus 1 is at right of A. Of course, I want to show that m plus 1 is just between A and B. So, but I have to convince you, for the moment, m plus 1 over n is just at right of A. Let's see why it should be at the left of B. Because if we take the number m plus 1 over n, this would be equal to m of n plus 1 over n. Now, by construction, m of n is less than A. And 1 over n is less than b minus A. So this would be less than A plus b minus A, which is just b. So the fraction m plus 1 over n is at left of b, as we claimed. So the fraction m plus 1 over n is a rational number between A and B, as in the statement. In a very similar way, we can prove the same property for irrational numbers. That is, no matter how we take two numbers, A and B, with A less than B, there is always an irrational numbers between these two numbers, A and B. Now, this means that no matter how small is the place we take in the real line, there are always rational and irrational numbers into that small interval of numbers. That's why we say that rational and irrational numbers are dense into the real line.